Welcome to the flock. Let's dive into using Hess's Law to calculate the change of enthalpy of a reaction using the delta H's of formation and solving problems just like this one. Stick around to see how it's done. Conceptually, you should understand that positive or negative delta H, or change in enthalpy, literally represents endothermic or exothermic reactions. If we go back to our enthalpy plots, we notice that the delta H, or the potential energy, is plotted on the y-axis. Therefore, we can say that this change in enthalpy is literally the distance between the reactants and the products. Therefore, if we were to look at this endothermic plot, we notice that it goes up. That should give us a slope or a positive delta H value. Therefore, we know that in our calculations, if we end up with a positive delta H, we have an endothermic reaction. However, notice the exothermic plot. Its line or distance between the reactants to the products goes down, just like a negative slope would. This means that you have a negative delta H value, and the negative there represents exothermic reactions. Therefore, if you do a calculation and end up with a negative, you know it's exothermic. So that means our hot hands reaction that we know was exothermic because it felt hot, if we were to do the calculation for it, should end up with a negative delta H value. Whereas our endothermic reaction, the cold pack example, should end up with a positive delta H value if we were to do the calculation for the chemical reaction. If you are given a delta HF value, that F stands for formation, by the way, this is a very powerful tool, because now say we had ammonia, NH3, and we were forming it, how much energy would that take? What kind of reaction would that be? Well, the answer is that it's a negative value. Who cares how big of a value? It's negative. Therefore, we know that when we form ammonia, that reaction is exothermic, meaning it would feel hot, or bonds would be formed in order to make ammonia. In contrast, if we wanted to make diamond, for example, which is just carbon under lots of pressure, we see that the delta H of formation value is a positive value. That positive means that to form diamond is an endothermic reaction. It requires heat in order for the diamond to form. Heat and pressure, that is. Oddly enough, as the diamond's forming, it should feel cold. So let's calculate for that delta H of the entire reaction then. We know that we have these delta HF of formations for individual chemicals, and that's going to be different for each single one. Notice the values are all different in kilojoules per mole. And notice that the state that the compound is in this case, gases for all of them, is also important to note. The value of the delta HF is going to be different depending on the state, solid, liquid, or gas. But before we start just plugging in numbers all willy-nilly, let's make sure that we would actually get the right answer, positive or negative value. We can start with our AA-AB bonds and predict whether or not the delta H of the reaction should be exothermic or endothermic before we do any math whatsoever. In order to use this method, we need to compare our reactants to our products. AA bonds represent any compounds that have the exact same atoms bonded together. Like in the case of oxygen here, there's two oxygens bonded together. So this would be an AA bond example. Whereas carbon and hydrogen are two different kinds of atoms. That would be an AB bond. Likewise, on the product side, we have carbon attached to oxygen. Those are two different atoms, so A and B. And water is composed of H's attached to an O. That's also representative of an AB bond structure. Recall that AB bonds are more stable because they are stronger bonds. So since they are more stable, that means they have less potential energy than their reactant counterparts. So if you were to plot this on a graph with potential energy on the y-axis, our reactants would be higher, our products would be lower. That means we have a negative slope, or a negative delta H value. We know that this reaction, if we calculate it correctly, should yield a negative value as our final answer. Another dead giveaway that this is an exothermic reaction is because it's a combustion reaction. It has products of CO2 and water and has a carbon reacting with an oxygen. Combustion reactions are always going to be exothermic. All right. So then how are we going to find the delta H of the entire reaction then? We need to take into account all of the delta H's of formation for each individual part of the entire reaction. So for CO2, we know that to form CO2 in its gaseous state, it's going to require negative 393.5 kilojoules per mole of CO2 present. We know for water in its gaseous state, it has a delta H of formation of negative 241.8 kilojoules per mole of water present. Now notice that there are 2 moles of water in this balanced equation, so we would need to multiply this by 2 in order for that to work out. According to our table here, oxygen in its gaseous state has no enthalpy of formation. So all we'd have to say is 0 for our oxygen, and there happens to be 2 of those, so you can multiply 2 by 0, but it still gives you 0. And then finally, methane, CH4 in its gaseous state, is negative 74.8 kilojoules per mole. All right, that's great and all. Now we've plugged in the numbers, but what do we do with them? Remember, we're trying to find a total here, the entire delta H of the reaction. That should hopefully make you think that we're going to need to add up something. We're going to add up the products together, and then we're going to add up the reactants together separately. This is where things get a little hairy with some students, keeping track of all those negatives and positives and who knows what, multiplying 2 negatives together and then adding or subtracting negatives. So let's draw this out explicitly in detail. 2 times negative 241.8 is negative 483.6. kilojoules per mole for water. And we'll be adding that value to the negative 393.5 coming from the CO2. When we add 2 negatives together, we end up with an even bigger negative. Think about it. If you were in debt and then you added more debt, you're in even greater debt. So adding those 2 together, we end up with negative 877.1 kilojoules per mole for the product side. The reactant side's pretty easy because all we have is 2 times 0 for oxygen, which is just 0, so we have nothing to add to, and all we're left with is negative 74.8. But now what do we do with those 2 numbers? So we're going to say product, that's this side, minus the reactant value. Now this is where it gets tricky because you want to keep track of your negative signs. Remember in this case, since we have a minus scenario, those 2 actually become positive according to the math laws. So then we can say negative 877.1 plus 74.8 should still yield a really big negative number, but less negative because we're adding 74.8 to it now. So we end up with negative 802.3 kilojoules per mole as our final answer. Notice that we did predict this should be a negative answer, and it was. So we know that we must have done this right, at least partially. So the thing that we just applied is called Hess's Law, and Hess's Law can be summarized as the delta H of the reaction is the sum of the change in the enthalpy of formation of the products minus the sum of the change of enthalpy of formation of the reactants. In layman's terms, it's the sum of the products minus the sum of the reactants. All right, so now that you've seen me try one, pause the video here and use the values from the table behind me to apply Hess's Law to this calculation. Ready? Go. Ready to check your math? Let's do this. Final answer for this question yields an endothermic value because it ends up being positive. If you forgot that 2 negatives added together makes them positive, please make sure you remember to apply all of the math laws in order to survive Hess's Law in chemistry. So we've been saying that this delta HF, or the heat enthalpy of formation, is always for 1 mole of a compound. Recall that the units are always in kilojoules per mole. That is implying 1 mole of the compound that's forming. But sometimes when you're looking for the delta HF of a chemical or a compound, it's just nowhere to be found. That's the case when you have an element in its standard state. these are delta HF values that are set to 0. We have all of the delta HF values from experimentation, and they are all in reference to the elements in their standard state. Now, I'm not talking about the state of Arizona or the state of Washington. I'm talking about the state it likes to be in, liquid, solid, gas. For example, oxygen likes to be in its gas state. That's its standard state, where it would be 0. And that's also why in the previous calculation we did, the oxygen gas molecule was 0 kilojoules per mole. We represent the standard state for the delta H of formation as a little knot in the corner. So you would literally write it as delta H, the change in enthalpy of formation in its standard state. That's what that little O in the corner means, set to 0. And since we determined the delta H formation of all these chemical compounds experimentally, it is also the heat energy, literally the enthalpy, that's given off for an exothermic reaction or used, absorbed for an endothermic reaction in order to form a chemical. Now that you know how to predict using AA and AB bonds, and how to calculate using Hess's law, and what delta H of F even means to begin with, go ahead and give this one more practice a try. Pause the video now. Let's check your answer. If you applied your AA-AB bonding rationale, you would have noticed there's AA bonding on the reactant side and there's only AB bonding on the product side. Whenever that's the case, we end up with products that are more stable and have less potential energy than their reactant counterpart, which means there would be a negative delta H on a slope or on a graph, meaning that this would be an exothermic reaction. So our prediction here is that we'll end up with a negative delta H of reaction overall. Now let's calculate to see if we're right. Remember, Hess's law is the products minus the reactants. And in this case, our reactant was a positive value, but we still have a negative in front here that distributes in. So that makes our overall answer an even more negative value. So we should have negative, which is what we expected, 1,516.8 kilojoules per mole for the delta H of the reaction. The overall steps you need to know to calculate the delta H of the reaction are as follows. Step 1, make sure you locate all of the delta H of formation, usually given to you in a table or in the back of your textbook. And remember that any chemicals or compounds in their standard state are going to have a delta HF naught of 0 kilojoules per mole. Step 2, look back to the balanced equation for the number of moles that are present. Recall that the delta H of formation is always in kilojoules per mole. That means just 1 mole. So if you have a 2 or a 3 in front of the chemical compound in your balanced equation, you need to make sure that your delta H of formation is multiplied by that coefficient. And step 3, last but not least, is just take the sum of all the products and subtract it from the sum of all of your reactants, which literally is Hess's law. In this lesson, we learned that exothermic reactions have a negative delta H value, due to the fact that when we look at the potential energy plot, we have products that are lower in potential energy than reactants, yielding a negative delta H slope. This means that the products will always have less potential energy than the reactants do. We also know that in exothermic reactions, we have bonds that come together, like iron plus oxygen coming together to form iron oxide. So we know that bonds are formed, and these bonds happen to be more stable. That's why the products are lesser potential energy, because they happen to be more stable. And since you have more stable products, the heat has to go somewhere, and the reaction releases that heat as energy. And since it releases the heat, it feels hot. Whereas endothermic reactions have delta H values that are positive. This is due to the fact that if we were to graph it on a potential energy plot, our reactants would end up being lower in potential energy than our products would. This results in a positive delta H slope, meaning that it requires energy, or it absorbs energy in order for the reaction to happen. And since it absorbs energy, it feels cold to the touch. We can also say that endothermic reactions will always have products that are higher in potential energy or have more potential energy than their reactant counterparts. And in order to get to a higher product state where there's less stability in the product side, we would have to have bonds that are broken, or bonds that come apart, like in the case of a cold pack, where the salts in here dissolve in the water, literally breaking apart the salts, and we feel that as cold. Go ahead and check yourself before you wreck yourself, and make sure that you can calculate the delta H of reaction of this chemical equation using the values in the table provided. Be sure to always apply your AA and AB bond rationale before calculating so that you can predict whether or not your final calculated answer should be positive or negative. It's just a good way to check and see if you did it right. And of course, never let your numbers run out in the streets naked. You want to make sure that you have your kilojoules per mole on your final answer. Please give this video a quacks up, and in chemistry, if you happen to be down on your luck, subscribe to the Duck.
No ducks, no glory.